This is Haotian. So I'm also a researcher from Apple, AI/ML team. So with the same team that's Joe's team. So today it's my great honor to present the topics, the large language models with the fine-grained grounding capabilities. Well, the previous two talks, Chuan Yuan and Joe talked, they have already introduced us the recent developments of the multimodal large language models and also introduced a lot of details about a series of the state-of-the-art works, starting from flamingos into some recent open source models like the Lava, like Sphinx, and also the closed source models. So for GPT-4 as well as the Gemini. So all of these models, they follow the same trend by inputting an image and also generating a large language model understanding visual features and also fed into the large language models. And then the large language models will try to interpret the input image based on the input text instructions, as well as they can also produce a textual response. So quite many bunch of these models follow this way. So they require the global image as the input. So I refer this as the global image perceiving multimodal large language models. Well, let's take a look at how these models works. So I simply feed in this year's conference logo to the MM1, which, yeah, I know like plenty of people haven't access to it, but I have the pleasure. So yeah, let's take a look at how what the model says. So it mentions about a lot of things like the Space Needle and also the word CVPR, which means the model was able to show us very strong capabilities on the pattern recognition, as well as a very strong OCR capabilities. And also beyond that, because we have the large language models as a very strong backbone, and the story also looks very reasonable comparing to the single captions by the traditional vision language models. So do you think you're right? Is that everything that you want to see? I don't think so, because if you take a look at some models input, the image contents become more rich, and then you ask this image, for example, like, please describe this image in details. And the models will try to output a bunch of these texts, while it also says like make some like incorrect answers. For example, like there are some benches and a fence in the background, which I cannot see it. While if you ask some like what is the girl in the picture is doing, and then they will say like the other people is picture around her. Probably that's right, but maybe not a lot of people will guess so. So we call this the object hallucinations, where we think that object hallucinations are inherited from the large language models bias. So these hallucinations usually we divide as the category hallucinations, the attribute hallucinations, as well as the relation hallucinations. Well, some other things that are also not perfect. So for example, like we know like the recent GPT-4, they have something called a visual prompt, where you can try to draw a circle around this image. For example, in here, it's a bit small, but it has a circle around some part of the mechanical bicycle. If you draw a circle around it, you ask the model what's a function of that. And the model tends to generate something, but actually that's not makes a lot of sense. It actually, because we draw about, if you know about mechanical bicycle, we actually draws the regions around the absorb, like shock absorbers, but it says this is kind of some like a gas bumpers. So, how should I deal with that? Someone's trying to record a video locally. Yeah, these are not secret.
Okay, cool.
Okay, thank you. Yeah, so some other things like if you want to actually know what are the locations of some specific regions inside the model outputs, and then we can specifically say like a Carpaccio example. You always find it on a Google verifications, right? You will see like where are the traffic signs in this image. So the ChatGPT, they are actually produced some like a reasonable text But if you draw these texts onto the image, you will see like they are not making a lot of sense. Bounding box are possibly have some offsets. And also, I don't think that GPT will understand the bounding box input actually. So yeah, up to here, I don't think the model works quite well. But if I actually speak at a NLP conference, I know the NARCO is currently ongoing as well. I will say, okay, you have such a nice large language models. I really appreciate that. But yeah, I'm currently speaking at the CVPR conference, right? I know a lot of people are working on the vision part. For a vision guy, I don't think I try to buy this because there are a lot of hallucinations, right? So I cannot see a boy actually or a girl actually in the background. And also I don't really, if I want to really know about the details of this image, and I cannot find any clues from it. Then we start to think how the vision plays a role into the multimodal large language models. So I think I think to reduce the previous issues, we think the visual grounding may actually be able to help. So for a lot of people, you may not really know the concept of the visual grounding. I guess I can start from a traditional computer vision task, for example, like the localization task. We have the object detection, we have the instance segmentations, as well as a lot of people also work on the visual language pre-training. You're also familiar with the vision and question understanding, as well as the image captions. So we think the vision grounding is kind of like a bridge between these. And also a lot of literatures, they have already proved that in order to achieve a general purpose vision models, you have to unify the localization task as well as the visual language understanding task. So here are a bunch of the previous work. So I will introduce like 3 works. I'll start from the GLIP and also GLIP V2 papers. So the works are, I call them as a unified framework for the detection and grounding. If you look at the architectures, so the GLIP models, they actually have 2 encoders, which one of them is the below one, a swing transformer for encoding the image features, as well as they have a BERT models, which they are like generating text features. And these features output from the encoders, and they go through some multimodal fusion blocks. And after the fusion, they're trying to, doesn't work. Hello, hello. Check, check. Check, check, check. Hello, hello. Hello, hello.
You can hear you.
Possible. Check, check, check. Hello, hello, hello. Check, check. Okay, okay. It works. Awesome. So let's get back to the topic. So we end just right at the multimodal fusion part. So these 2 features come from the 2 different backbones, and then they go to some multimodal fusions. So after these fusions, so the text part actually comes from the word embeddings from the BERT models, and also the vision part actually generates a lot the vision embeddings from the vision proposals. And all of these features, they're trying to do a contrastive image text alignment. And these features will be used for the alignment loss as well as the localization loss. So regard this model as a pioneering model for learning the object level, language aware, and semantic rich representations, where it also benefits from the detection data and grounding data, and also possibly the pseudo label web image text data for scaling up. And these data together, they can boost the grounding performance. So you can see there are a bunch of tasks the GLIP and GLIP2 models they can have already accomplished. First is the traditional object detection like COCO, and also segmentation like COCO mask. Or they can also do the phrase grounding like Flickr 30K, as well as they can also do zero-shot transfer to some object in the wild task like object object detection in the wild. They can also do some very simple reasoning segmentations. They can do phrase cut, as well as the traditional vision language understanding, like the visual question answering, as well as the COCO caption. Well, there's a follow-up works for grounding dino. I think a lot of people have familiar with this, and then so far it's using this tool to do some open vocabulary object detection as well as grounding. So I can think of the grounding dino as an improved version for the glib and glib v2, where it mostly focuses on boosting the performance. We know like the grounding is actually focuses on two aspects. The first is the semantic understanding of the input query. The second is we need to find a bounding box, so it requires a very strong localization capabilities. So for the grounding dino, it improves. It doesn't use the retina net and also a bunch of dynamic head as the glib use. So they actually use a very superior transformer architecture detector, which is called dino, as a better detector to generate the bounding box. And second, they also in their literatures, they also find if you have more or better image text feature fusion, that this will also lead to a more understanding of the semantic meanings. So incorporating these two, so this will lead to a very superior performance for the grounding. And later, there's a word called SEAM, which the full name is segment anything, anywhere, all at once. Very global pictures, right? Yeah, so I consider it as a single generalist approach for pixel level understanding. So it doesn't actually output the region like a bounding box feature outputs, but it actually focuses on more like semantic, like a pixel level understanding, like segmentation masks. So for the SEAM, it actually introduced a bunch of the visual prompts. So it doesn't only output the semantic masks or the bounding boxes. You can also take a set of the visual prompts as the inputs, which are not the textual inputs. You can take in the points, you can take in the box, you can also do the scribbles. You can take whatever free-form shape into it. And as well as they also introduce something called the memory prompt because they're using a decoder architectures. So this can enable them to interact with the users in the multi-rounds because the previous input, they have some memories into it. Of course, I just introduced like they actually can also give us semantic labels to any predicted segmentation task instead of only outputting the bounding box. Well, these are the work actually before this year until 2023. So we can see the trend actually becomes, I've listed a bunch of the related work. I only cover 3 of them, but you can see like I listed some tiny difference between them. They're using a more like external detector to improve the localization performance, as well as it also needs to understand the query's input. So that's why they need also the strong encoders, especially for the text encoders. They are generating from the pure BERT, like kind of like self-attentions towards the decoder like models. And also the third thing that's about this area is everybody is focusing on the unifications. So the unification here I listed only inputs and outputs, where I mean like you can feeding a different visual prompts as well as generating the free form like outputs, bounding box or segmentation mask. But also like there is a unification trend on the architecture as well. You can see like a lot of like works there throw away the convolution architectures and then also using the transformers as the mainstream. So I've covered several works, so let's possibly take a short break and also give us some time to think. So what we have covered so far, first of all, we have seen the typical visual language models or the multimodal language models actually suffer from 2 very severe issues, which is the object hallucinations as well as the spatial understanding. And also we think the transitional vision ground concept maybe elevated this above issues. And third thing that I have listed several existing works, and also I introduce a bit details about them and some trends like ongoing works. But the entire field is changing really fast with the breakthrough of the large language models. Actually, I see like many people are moving their trained from the traditional transformers. And then we have the large language models. So the thing is become like how the grounding will benefit the large language models. What the things like what magics can actually combining the grounding with the large language models can bring us. And how the most important thing is how to integrate the grounding into the large language models. So first of all, I want to introduce like why we think we have a potential like by combining the spatial understanding with the multimodal large language models. So first of all, of course, it enables some new functions, right? So because we have the models as we can have the inputs as the regions as inputs, so the user will be able to specify to which regions or which objects, and they can ask the models for help. And also because sometimes the textual output only have plain text, but we actually don't know which object or which things they actually in the image are talking about. So we also need the models to localize or ground particular objects in the response to help the user to find them or to guide them. And of course, the grounding capabilities can also help to generate a much better vision language models. For instance, like they can, because they have the bounding box output on all the things they have mentioned, so it reduces the hallucination possibilities in the text outputs. And second, it becomes more trustworthy because we think that because we have the grounded evidence of what things are talking about. And third is that we are having a more open vocabulary concept because with the very, very large scale large language models pre-training, we have more concepts like by just using maybe the contrastive laws or other different type of the pre-trainings. Third thing that I want to mention is that it also enables a lot of new applications. The one thing I can think of like the phone, the VR, AR, Vision Pro, like Apple Intelligence, right, recently here. And second is the 3D embodiment, especially these grounding things can help the robot to guide themselves and also try to grab whatever they want. And third thing is about the medical assistant. I think Chunyuan has already mentioned the LLM works. So seems like we combine with the multimodal large language models. So our problem will be slightly different from the traditional visual grounding concept. So I regard the spatial understanding into the two different tasks. The first is called the referring. So in the multimodal large language models, because we only can enable the text as the input or the tokens as the input. So the input representation, I form it into like we have the image tokens, we have text instructions tokens, as well as we can also have some region tokens. It can either become the continuous features from the text vision encoders, or it can just become some discrete coordinates. Right. And so the model is required to understand the referred regions and also respond to the instructions. So the input regions can be different types, just like what we have seen in the STEAM paper. It can be a point, it can be some bounding boxes, or it can be some scribbles. If you see this example, you ask like what is in the region and what is it used for. So previous STEAM cannot be able to understand it because it doesn't have the large language model as the output. But if we combine the grounding with the large language models, so this will only trigger the multimodal reasoning capabilities. So the models will generate more natural styles, like when we communicate with the models. Yeah, of course, like the second example shows like which movie characters are in region 1 and region 2. Traditional visual language models cannot do that because they have not seen Harry Potter, Daniel Radcliffe, and yeah, Hermione in a Harry Potter. And second thing is about outputs. So we refer that to the grounding. So the output representation is way simpler because it can just represent as a text response by having the regions into the textual response. So the model is required to localize the objects in the image when also mentioning them in the response. For example, different from a text model, if I want to ask how to make a sandwich, the text model will have different kinds of outputs. And possibly you don't have all of these foods or have these ingredients available. But if you have a grounding with multimodal large language models, you ask the model how to make the sandwich with available ingredients provided in this image. So the model will first recognize all of these things and then generate basically like the things upon that, right? and also it will tell you which exactly things are like where. So there are a bunch of works for fine-grained region level multimodal large language models, which are different from the global image perceiving multimodal large language models, as we previously mentioned. So there are several works like GPT-4 we have Ferret, we have Cosmos 2, we have Shikara, and a bunch of works. So these things, in addition to the image and text as input, we also have the region or the pixel as input. And as well, for the output, we can also generate the regions as well as the text simultaneously. So I want to introduce some two pioneering works, which are the first two works that implement the kind of like the concept. The first one is called Cosmos 2. A lot of people have familiar with this. So Cosmos 2 actually focuses on the grounding. You can see they have the location tokens as input, as well as they also have location tokens as the output. So beside that, they're adding some kind of like new vocabularies aside of the original text tokens, which are inherited from the large language models. So because they also need to learn a very well representation for these location tokens. That's why they constructed a web scale grounded image text pair, which they also construct, have a lot of like regions instruction into the original data. They construct about 19 million data into it, and they train this model. Turns out it works pretty well. And second thing is about Shikara. The Shikara is, I think, is a concurrent work with the Cosmos 2. So what the Shikara does the grounding is slightly different from the Cosmos 2. It also has the grounding as the output, but instead of using the location tokens, it has, you can see like 0.392, those kind of like a traditional, like numerical numbers into the, just similar as the text outputs that coming from the large language models. So they tend to use, they also shows a very interesting study by comparing using the location tokens as well as using pure numerical numbers. They find like if you just directly use the numerical numbers, it will not decrease the performance. But actually, they also find that because we don't have additional vocabularies to be learned, so that's why you can just directly use the numerical numbers. That can save you a lot of training time, as well as you don't need to construct this web scale grounded image text pairs. They also generate some more elegant representations. Well, another work is called Ferret. The Ferret is, I can think of as a more unified models where we not only have the discrete location tokens or the text tokens as input, but we can actually enable the different features or different kind of like visual prompts into the models. So we define the hybrid representations as the region name plus the discrete tokens, as well as the continuous features. So for the, we know like for the point box, we can represent as the discrete coordinates. But what if the user actually draw something like, for example, the tail of the cat? You need some other things to represent the coordinates or better represent these features. Another more severe case is that on the right side, you have kind of like a gun on the left side and also a knife on the right side. But if you use the pure coordinates, I mean the bounding box coordinates, these blocks will very likely to be overlap and trigger as the same. But in addition to that, we also introduce the continuous features, where these features will be more like aligned to the thing that like the people have referring to. Yeah, for discrete tokens, we represent the point as the pure XY points. Also the box, we can free-form shape, and also they have a bounding box attached to it. So it's called XY, X1, Y1, X2, Y2, which use the top left and also the bottom right points. So we tokenize these just similar as what Shikara do. We tokenize them by the large language model tokenizer, and we feed into models. And second thing is the continuous visual features, which is different from the previous two works. So we introduce a visual sampler, which they will be able to extract and also summarize the visual features of the referred regions. We actually point to the circle, and then we flatten them into a single vector embeddings, and then we actually input them with the previous things. So the example of this data, you can see the regions. If we ask the question, what is the region? and you have discrete set of the tokens coordinates, as well as we have a special token to represent as the features. So the output is set of the grounding. We have the bounding box as the output. So for the model architecture, we slightly modified on the Lava style architecture, where we use the image encoder as the clip VIT large 14, and then logging models, we used the open source model called the Vicuna V1.3 at that time. And we also have a specific module, which we call the spatial aware visual samplers. And this model will try to take in the hybrid representations and also generate the grounding outputs. So we use the next token prediction as a loss because we don't introduce any other vocabularies. So basically, we also fix the image encoders and also update the rest of these other modules. So yeah, I just introduce a bit details about how our spatial aware visual samplers are constructed. We use something like very similar to the point nets. So we actually first sample 512 points inside the region features, inside the regions from the feature maps coming from the clip features. And then we have two blocks, which we go through each one by one. And then we first downsample these numbers of points, and then we find the k nearest neighbors about these centers. And then because we think like the center of the points will make more weights contributes to the final results instead of like surrounding features. So we also fuse these neighbor features, and then we do like pooling. So finally, we have like a downsample from 512 towards 32 points. And then we linearly projected these features into the LM embedding space. And this space will be concatenated with the discrete tokens and then feed into the large language models. So to train this data set, these are slightly different from the Lava type of the data sets, which are not exactly the pure image and text pairs. We introduced this grid data set, which we called as a ground and refer instruction tuning data sets. So this is a more hierarchical, more unified format, and also it has more bunch of instruction following as well as some samples for the robustness. So total data sets are not that too large. It only consists about 1.1 millions, which they are mostly focused on object levels, where you have the input as the regions and output as the regions. And also you have relationships. You can have multiple bounding boxes. You ask about the relationship between them. About the regions, what are something like not objects, but actually the region part. And then detailed reasoning. We actually use the GPT-4 to curate these data, where it can also embed some reasoning into the region, local region concepts. And finally, the robustness. Sometimes if the object is not exist in this image, we ask the model to output no. Yeah, here are some few short examples. So it's different from the Lava style. We not only feed in the pure bounding box as well as what the objects, but we are also feeding in the region descriptions as well as we have like the relationships. And then we trigger the ChatGPT. Purely they're just everything was formatted into the text. And then we trigger the ChatGPT to give a set of the conversations. And we use the set of these conversations as a ground truth to train our models. And another thing I want to mention is about the spatial negative mining. So we have two types of the negative data, which first is we call the image condition category localizations, where we ask the model to localize an object class that are in a common vocabulary, but actually not in this image. For example, if there are a cat in this image because there is a dog, so we ask the model to output, no, there is no cat, but there is a dog in this image. And second thing is the semantic condition category localizations. So we actually want the embeddings to be slightly different. For example, if the dog is not a husky or not a gold retriever, we actually ask the model if there are a gold retriever in this image. Possibly all of these models will try to, other grounding models will try to localize. Okay, I found the embeddings very similar to the dog here, so I just gave it a bounding box, but that's not ideal. So we ask the model to localize an object class that is semantically close to an existing object in this image. Well, for the evaluation part, we have the conventional task as well as we have open-ended kind of like evaluation. So for the referring task, we ask the model to, we first circle out the regions and then we ask the model to predict the class of it. We can see how accurate the models will, we want to evaluate how accurate the models will try to predict. So we also have the three type of formats. We have the box as input, we have the point as a test, like also the freeform shape as a test. So we use Elvis because Elvis has such a large open vocabulary sets. So the random guess about the point, box, and freeform is a binary classification, so that's around about 50. And you can see comparing to other models I have mentioned, like GPT-4-RY, Cosmos 2, and Shikra, they are able to take the discrete input, but the ferret at that time, it outperforms these models. We also have the conventional object grounding or phrase grounding sets, which we focus on the Raphcoco sets and also the Flickr 30K phrase grounding sets. So at that time, comparing with the traditional models, like like MDTer, like Unitat, those models, and also the Shikra models, the ferret outperforms them. Another thing, because previously we mentioned about the vision task, like conventional vision task for referring and grounding. So here I also introduced, because with the help of the large language models, it can also do very interesting reasoning capabilities. So we want to mostly focus on the fine-grained reasoning capabilities. So we introduce these three tasks about, we call the referring description. So we kind of like describe a referred region and based on its interaction with the surrounding objects. We also have another evaluation task for referring reasoning and actually reason on top of one or more referred regions, whether it's correct or not. And also the models are able to output grounding in the conversations. We want to see like whether these outputs, also the box, are related to the object they have mentioned. Well, you can see like qualitative examples of the output. For example, if I have this circle, if I have this square, what is the purpose of the object? And I also try to sort out like give a bounding box around it. So ground truth is generated by when we input the box as well as the region description into GPT-4, and it will generate this object as a box where it also sends reasoning out of the image, like a box I typically use for whatever things. And if you feed into lava, because lava doesn't have any spatial understanding, so it just basically hallucinates. And for Cosmos 2, it can extract the referring, they will say, but it's not really accurate. It says the purpose of the object is to track birds to the table, which is not exactly right. And also the Shikra also does not make sense at all. It says the thing is to keep the birds away. The way that ferret says the object is a bottle, which generally used to store or dispense the liquids like water, juice, or other beverage, which very close to the ground truth outputs. Yeah, we also compare with, at that time, we also compare with the GPT-4V. We see like the ferret on the referring and grounding task, they actually outperform the GPT-4V because GPT-4V at that time doesn't have any spatial understanding at all. If you refer to, for the referring, we actually also show this mechanical bike examples. For possibly the larger areas, if we ask the GPT-4V, it will try to give a very possible answers. But very, very small regions, the one I just showed like on the shock absorber, doesn't really produce a very reasonable outputs, as well as this CAPTCHA, where I think the AGI things investigate here. So if you ask where are the traffic lights in the output, the ferret will try to give a set of these discrete outputs, and then if you try to draw them into this image, you can see it finds most of this image. And yeah, you can click them and to avoid and to pass this kind of verifications. Well, recently we introduced another work, which is a which is a improved baseline for the referring and grounding with the large language models. So it shows a substantial improvements over the fine-grained region levels, as well as we can also see the region level benefits can also be transferred to the global image level task. We have some benchmark performance comparing with the Ferret V2 with the Ferret V1. It has shown various substantial improvements. For the left qualitative examples, for the referring, you can see if I refer to like a region on the left side. Yeah, I think that the mic doesn't work. Hello. Hello. Okay. Okay, perfect. Thank you. Yeah, for the referring, if we refer a very small regions on the left side, I'm not sure if you can see it very clear. If you ask the Ferret V1 models, it will say some apto, which is slightly, I think it's correct, but slightly, I think there's an offset. But actually the word is the great. Ferret V2 are able to predict it. And also grounding, if you ask some models like, is there any way like I can make the people cool in the summer? The Ferret, I think it's able to detect those vehicles, is that vehicle has air conditioners, but that's not what people want, right? So the Ferret V2 will generate more precise grounding outputs where they can find these very small air conditioners on the buildings, and then they are able to find all of them. So you can say like, with the air conditioners, people's can make it cool during the summer. So how we achieve that? I think first of all, because we have introduced a bunch of works on the traditional vision language retraining. So we know like there are two things very critical. The first of all is that we want to have a better detector, right? But because we are actually using the pure text outputs, we don't have any embeddings we cannot concatenate with any hex. This unifies our detector and becomes more elegant. So then another way is just to scale up image resolutions. I think this is mostly critical to the multimodal large language models areas. So the resolution, we know that resolution is even more critical comparing to the like a global grand task. So typically, like with current large language models, we can actually do two ways. The first of all, I call it the direct upsampling, which the way of doing that is that you interpolate, you have a larger image as input, and then you interpolate, because CLIP is trained on 224 or 336 as a pre-trained models, you just kind of like doing the upsampling by interpolating the positional embeddings, and then during the training, you try to bypropagate towards the vision coders and trying to train this pre-trained, fine-tune this pre-trained image encoders. There is another way, like you can either fix the image backbone or freeze it, but you can use any resolutions as Chen Yuan and also Zhang, they have introduced. You kind of like split this image into multiple patches and you feed each patches into the CLIP encoders and you generate all of these global patches as well as the sub patches. And you concatenate them and you feed into large language models simultaneously. So we did a solid analysis on these. We choose the referring task, we choose the grounding task, as well as some task, global tasks, but require some fine-grained understanding, for example, the text V2A, as well as we have open-ended, the Ferret bench. We try to see which one is better than which one. And through our studies, we find generally, if you want to do the scale up for the large language models, actually two outperforms one a lot. But this also makes sense, right? Because if you try to fine tune the image backbone, you are trying to disrupt the semantic pre-training concept from the CLIP models. So this will actually hurts a lot of performance when you're transferring to an open-ended dialog. And second is because in the Ferret, the grounding is just purely linearly the outputs into the pure text format. So everything is dealing by the large language models. So this can, if you do that, if you can effortlessly combine with the Ferret grounding. Another thing about is the multi-granularity visual encodings. The vision people like to study about whether previously we used the CLIP encoder, I think for most of these works. but if there are anything like other vision backbones may be able to help. We try to switch the clip encoder with the DynaV2 encoders, but purely maintain the same architecture as the Parrot, but doesn't make a lot of sense. So we think about the reason why the DynaV2 and clip doesn't comparing to clip on these tasks. But actually with the natural scaling, we are able to merge these two features together. So because due to the annual resolution scaling, we actually divided these into the different patches. But we find like due to the clip training, it used the center crop, and also due to its pre-training, it only sees the global image as well as whole text. So we think the clip encoder is more benefit for encoding the global patch. But for the split patch, actually, if you think about the clip encoder, actually in the pre-training, it doesn't have these kind of like different props and also doesn't see any partial images. Does the clip work that well? Possibly not. But because of DynaV2, because they have different augmentations during the pre-training, as well as they are leveraging a more self-supervised way, they can trigger the localizations of these tasks. And then we use the DynaV2 to encode the subpatches. And finally, we use the global patches concatenated with the subpatches. And then all of these will be fed into large language models. So this is kind of like a specific design of the Ferret V2. And third thing, because we have an additional DynaV2 encoders, so where can we get we know that there's a projector between the encoder as well as large language models. So how to train this projectors? So previously in the Ferret, we only have the first stage, which is like alignment stage. The third stage, which is more like instruction following stage. But for Ferret V2, we introduce another stage. We call it the high resolution dense alignment, because we think the transition from the low resolution pre-training to a high resolution pre-training, actually you need some data or some phrase to adapt to it. And second thing is that because the projector 2, which aligns the DynaV2 encoder as well as the large language models, need some initializations. So we find so we use the data from the LVIS dense kind of like captioning or referring. So for example, we constructed this dense referring data. We have please classify the objects in the following locations. You can see we have a bunch of these dense regions. And then the answer, we have the classification labels concatenated into the text. As well as we also have the dense grounding. So the question will be, please localize all the visible objects in the image in a raster order, like a scan order. So this answer we constructed, the objects are the first, for example, cat, we give a coordinates. Second, a dog, we also attach a coordinates to it. So there are several benefits I have already mentioned. It can train the projection for the projector 2. It can also have a more like a smooth transition between the low resolution and high resolution pre-training, as well as because we have additional spatial aware visual samplers, it needs to have the continuous features to be able to train. So the second stage also, we can have better initializations for the spatial aware visual samplers. By looking at its performance, of course, we compare with even stronger grounding models. This time we also included grounding dyno, which is previously the state-of-the-art models for the phrase groundings. We actually outperforms it. And also on the referring conventional benchmark, previously only have the LVIS, but due to the LVIS, it only have like 600 or 800 image resolutions. But we want to see like if Ferret V2 can actually find really, really small objects given even higher resolutions. So we take the image from the SA1B, which are used for the same segmentation purposes. So we actually on the SA referring benchmark, we also can get a very substantial improvements on that. Thirdly, we also transfer this fine-grained task to the general task. We can also see the fine-grained task also have a lot of benefits for these conventional like multimodal large language model benchmark as well. All right, so I I have mentioned about a lot of like a region level multimodal large language models. Of course, there is the other fine-grained pixel level multimodal large language models. So here I introduced the Vista large language models, which it's kind of like not only predicting the bounding box, but also predict the mask as well. But the mask is kind of very tricky because the mask we are, if you represent the mask as some kind of like polygons, you will have very, very long context. But the Vista LLM is introducing a very interesting way called adaptive sampling. They are trying to like kind of like downsample the points of these polygons and they recover it back. So they're also using the text as the output, but they're representing the mask as a shorter context. Another work, which I think is concurrent work with the Vista LLM, which is called the Lisa as well as the Glenn. So these two works also focusing on the pixel level outputs for the semantic mask. But the difference is that so it's not using the text like a sequence of these text to decode the mask, but that's actually using some pre-trained decoder from the same. So with the large language model outputs, you can have those embeddings. So these embeddings can be actually effortlessly combined with the same decoder. You can think of it as more like kind of like a prompt from the large language models. So this prompt comparing to just the visual prompts, it possibly has more reasoning because it combines with the large language models. So these two models will also be able to perform some reasoning segmentations. And finally, I want to introduce some video-based region-level multimodal large language models. I think that the trend is kind of like evolving. Many people are focusing on image, and also they can transfer the image to the multi-frames or to the video part. So there's a word called the PG phrase grounding video large lava. So different from the traditional models or the image multimodal large language models, and they kind of like having the multiple frames as input. So how they extract the feature, because they have multiple frames, so they're applying some, they use some video encoder or video encoder. They apply some spatial or temporal pooling, try to reduce the multiple frame tokens. And then afterward, when they generating the embeddings, they also have the entity matching modules, where these entity matching modules is very similar to the GLIP and also the grounding dyno, where they have the response, they extract the tokens, they also have the features when they try to match them together. Another thing they did is that because the video always comes with the audio inputs, so they also have those aligned audio inputs as well. Well, I have introduced a bunch of these models. They work really great and they're really fancy models. But how these models will be able to benefit the people's living in the world. So as a guy from Apple, we care about the new applications for the UI understanding. We think these capabilities will enable the more interactive and more intelligent UI experience for the users. So different from many models, they're working on the natural image, but this time we focus this on the screenshots. But these screenshots can actually come in from the Android or coming from the iPhone. So we have those annotations, and we divide them into some elementary tasks as well as some advanced tasks. So we have a model called the Ferret UI, which is actually work based on the Ferret. We can see a bunch of these tasks the Ferret UI are able to do. We think that if you user will tap on some regions and will possibly like generate some outputs from that, and also the output have some ground. The Ferret UI also has some grounding capabilities. Well, if you want to accomplish some tasks, you need to find the specific button or specific actions to achieve that. So the Ferret UI are able to do that. And also regarding the advanced tasks, you can also think if I want to purchase something, what things should I do step by step? And the Ferret UI will also be accomplished on those tasks. So we think this multimodal large language models, I think this kind of understanding is different from the text. where you can simply input these meta information from the websites or from the screenshots and you send into it. But sometimes we find like it's not not ideal because, for example, like a shopping apps or some like podcasts, there are some image contents where you also need to get an understanding of both image contents with the buttons together, and where these contents are not always available through the metadata. So there is another example. You can see how the Ferret UI works on the iPhone screen. So besides the UI understanding, I think there's also one possibility trained that we can leverage the 2D grounding models to 3D, and a lot of works have already started, like the 3D LLM. I guess that's a pioneering work. They can do the 3D captioning, 3D grounding, as well as a bunch of these tasks, where they also involve some embodied AI tasks like object navigation, visual language navigation, embodied QA, a lot of stuff. I think this is also a future trend because actually we want to study the whole like spatial intelligence as recently proposed, right? So I think the spatial intelligence requires a really great spatial understanding, and this, I think the 3D and also embodiments can benefit from that a lot. Yeah, finally, there's our short conclusions. So for the takeaway message, let's summarize what has been covered. So personally, I think the referring and grounding capabilities are also the core task of the recent multimodal large language models. And also we introduced a bunch of different kinds of the fine-grained multimodal large language models where they are focusing on the spatial, on 2D. You can have the points, boxes, or masks as inputs for the outputs, and also some video temporal grounding. Like we can also focus on the multi-frames for videos. And third thing is that if you enable the referring and grounding, it can actually enable a lot of new applications as well. Like the thing that the Ferret UI has demonstrated, as well as some 3D grounding models they also demonstrated. I think the future challenge actually still a lot of things to work on. So for example, because if we want to find really, really small objects, given such a high resolutions, because if you split the patches and then feed into the LLM, we always have a predefined context window for the large language models. You cannot feed in whatever, like how fine-grained the visual features are. So definitely, I think the high resolution need to be supported, but it needs to be supported in a more clever way with the context of the large language models. And also because we have more larger context windows, we have more image tokens involved, and also the training efficiency will become very critical. And another thing I haven't listed here, but I think is really important is that because I think so far we call the multimodal large language models, it's because we have a very large pre-training language model as a backbone. But for a vision guide, I think we should always think about how the vision can be actually compatible with the large language models. I don't think the large language models will be entire over everything. So in the afternoon talk, I think Jianwei will have a very detailed look into the vision, how the vision actually helps the multimodal large language models. Stay tuned. And fourth thing is that, some tasks actually requires the fine-grained understanding, where some tasks possibly not. If I just want to ask, what year is this person born? There's not a lot of things to be grounded. So I think a more super alignment way of triggering this grounding capability is also a very interesting topic to be studied. Okay, I guess that's everything I want to cover today. Thank you.